Yeah. Hi, guys. My name is Patrick McCorry. I'm an assistant professor at King's College London. And actually, I'm getting involved in a startup that's trying to solve the watchtower problem for layer 2. So raise your hand if you know about the watchtower problem. Some people too. Okay. I'll briefly talk about it here before during my talk. So what I really want to focus on is, I guess the previous two talks sort of give you all excitement about, the future of off-chain and the future of Lightning and the current plans that are going to get implemented. I'm going to go a bit to the past and talk about the payment channels that were around from 2013 to 2015 before the Lightning Network paper actually emerged. Okay, so that's going to be the focus for today's talk. What I should also mention is that my research is funded by the Ethereum Community Fund, the Research Institute, and the Ethereum Foundation grants as well. Okay, and after I talk about the historical perspective, I'm also going to lean on to some of the problems that Lightning faces at a protocol level. So regardless of how you implement it, it will always face these problems. And hopefully, by changing Bitcoin, we can fix some of those problems as well. So how do I do full screen? Oh, that is crazy resolution. Look at that. Okay. Cool. Okay. So who's excited for Lightning? Raise your hand if you're all excited. Look at this. We should all be excited. Look, that graph is incredible. I mean, if you go to a VC with that, of this graph going up, you'll raise lots of money. So that's really cool. We should all be excited that Lightning actually exists and has real users. Okay. Now, before I get into it, what I want to talk about is that there's two components to a network. There's a channel between two parties who can then transact back and forth. And then given a set of channels, you can then build this entire network that we see today. Now, what is a channel? A channel is a really basic idea. We can imagine there's two parties, and every time they do a payment, both parties have to agree to this. Now, a channel should give you two guarantees. The first is safety. If I have one coin in the channel, and I have a balance of one coin, I should always get the coins I deserve back. It's non-custodial. Nobody can steal my money. And it's also guaranteed liveness. If someone has promised me a conditional transfer, if I reveal a secret, you give me one coin, I should always be able to self-enforce that condition myself. I should always be able to complete the next state transition and get my coins that I deserve. Now, off-chain's really exciting. Okay, channels are super exciting as a scalability solution to the cryptocurrencies. Why is it a scalability solution? It doesn't increase the network's throughput. That's really important to say. Bitcoin will only still support 10 transactions per second. But what's really exciting is that it simply reduces the network's load. Two parties lock in coins. They can do 200 plus transactions off-chain locally amongst themselves. And then one transaction to close the channel and get their coins back in Bitcoin. And that's really cool. We no longer care about blockchain latency. You no longer wait around for 6 confirmations or an hour. And in a channel between two parties, there's no fees. They're just transacting locally between themselves. Of course, when you get a network of channels, that's when fees start getting introduced again. But we'll ignore that for now. And the whole point is that we should also retain the similar security guarantees as if we just did it on the blockchain. We should have very similar security guarantees as doing a normal Bitcoin transaction. Now, before Lightning, we had Spielman channels that are one-way payment channels. Alice can pay Bob, but Bob can't pay Alice. We had duplex micropayment channels by Christian Decker in 2014. And then we got Lightning channels. And I'm going to go through each channel very briefly for the next 10 minutes. And hopefully what you're going to see is a pattern emerging that I'm not going to reveal right now. Okay? Now, what's the big problem these channel constructions are really trying to solve? How do we update the state of a channel? And in this case, this is just the balance of Alice and Bob. Every time Alice pays Bob or Bob pays Alice, the new state of the channel is just their balance. How many coins does each party deserve? So a Spielman channel is really straightforward. You have Alice, there's the little doll, you have baby, the Bob, the baby, and they're going to set up this one-way payment channel, okay? So how's this going to work? Alice is going to deposit in one coin, and this coin can be released if one of the following two conditions are satisfied. Alice will always get her coins back after time t. The channel expires, there's no activity, she's always refunded. Or if Alice and Bob cooperate, they can spend the coin anytime before time t. Okay? So in the refund case, the transactions in the blockchain, channel set up, there's no activity. By block t, Alice can always be refunded. So how do the payments work? Okay, the payments are really straightforward in a one-way payment channel. What Alice is going to do is she's going to pay Bob 0.1 Bitcoin. How does she do this? She signs a new Bitcoin transaction where she's going to give herself back 0.9 Bitcoin and she's going to give Bob 0.1 Bitcoin. She signs this and then she gives this to Bob. Now, Bob can make one of two decisions. Okay? Bob could either sign this immediately, broadcast it to the network, and redeem his 0.1 Bitcoin. Or Bob can just keep a secret. Bob doesn't have to reveal this to the network immediately because he's guaranteed that Alice can't get her coin back until time t. So any time between now and time t, Bob could broadcast this transaction and get his money back. So for now, he just keeps a secret. He doesn't broadcast it to the network. And then boom, there's a second payment. How does this work? Alice creates another Bitcoin transaction where she's now going to send Bob 0.5 Bitcoin. What she does is that she creates a new payment transaction where she'll give herself back 0.4 and Bob's going to get 0.6. She signs this, gives it to Bob, and again, Bob can make that exact same decision. Does he sign it and broadcast it to the network? Or does he just keep it secret for now? And of course, this keeps happening until eventually Alice has no more coins in the channel and Bob has one full Bitcoin. Now at this point, it's a one-way payment channel. Bob cannot pay Alice back. So the only decision Bob can make is that he can sign the transaction, broadcast it to the network, and redeem his full Bitcoin. Okay? So we call this technique replace by incentive. Bob will only broadcast the transaction, he'll only sign and broadcast the transaction that will pay him the most coins. And that's really cool. Okay, so he just broadcasts that out. He gets his Bitcoin. The channel is closed. So according to the Bitcoin network, there were 2 transactions. Really off-chain, there were 3. But there could be hundreds. There could be thousands. The network has no idea about these payments. But what if we want a bi-directional channel? How can Bob send the coins back to Alice? Now remember, this is pre-Lightning. We're now in 2014 world. Okay? And what we're going to use is something called replace by Timelock. So every time the payment direction changes, the channel expiry time will be decremented. Okay? So again, the funding transaction has 2 conditions. Either Alice gets refunded after block 20, or if Alice and Bob agree, they can spend the coins immediately. Okay? That's when the refund's going to be valid. Now, when Alice sends Bob 0.1 Bitcoin, what she's actually going to do is include a new expiry time on this channel. Okay? So you can see that Alice can get her coins back, 0.9 coins back, and Bob's going to get 0.1 Bitcoin. This transaction's only valid on day 19, block 19. Okay? Now, when we change payment direction, when Bob wants to pay Alice, he'll sign a new transaction. Perhaps he's going to refund the 0.1 Bitcoin. And now what he has to do is reduce that expiry time, the T18. So this transaction is valid on day 18. Does that make sense to everybody so far? Who thinks this is a bit complicated and convoluted? Okay, it's not too complicated. Cool. Okay? Now, this is the important bit, okay? Bob has to be online for block 18 to broadcast it. Otherwise, payment 1 could be broadcast at block 19. So we're using this timestamp and reducing this expiry time to ensure the latest transaction can always be broadcast before any previous payment. Now, what's the problem of this approach? Okay? Oh, I hear myself. That's exactly the problem. Okay, the issue is that every time we change payment direction, we get closer to present time. So if we change payment direction 20 times, we have to close the channel today. And that's really annoying. Now we can't do rapid bidirectional payments because now we're eventually going to reach present time and have to close the channel. So duplex micropayment channels in 2014 tried to solve this problem. How can we support bidirectional payments without quickly, reaching present time? So who's heard of duplex micropayment channels before, by the way? Some people have. It's a bit of a quirky protocol, so I'm not going to fully explain it. But the idea is fairly straightforward. It has two components. There's two one-way payment channels. Alice can pay Bob, and Bob can pay Alice. Two one-way channels, as we just seen before. Now, the point here is that when one of these channels runs out of coins, maybe Alice has sent all the coins to Bob, and she can't send any more coins. Okay? What this protocol will do is destroy both one-way payment channels, recreate a new pair of one-way payment channels, all off-chain. So that's cool. Every time the one-way payment channels run out of coins, we destroy them, we create a new one, we reallocate the balance as appropriate, and then we start using the one-way payment channels again. Now, to do this invalidation, they have this invalidation tree that basically I'm going to show in a second. Okay? So that's the one-way payment channels there. Alice to Bob, Bob to Alice. You just do all your payments in the one-way payment channels as normal. Okay? As you see. And now we've exhausted our one-way payment channels. Alice can't send any more coins to Bob. Bob can't send any more coins to Alice. But Bob has a coin and Alice has a coin. So now we want to destroy these channels and recreate them. Okay? And we do this completely off-chain with this invalidation tree. So every little node, so 100 days, 100 days, 100 days, is a Bitcoin transaction. And then at the end of the leaves, there's these two one-way payment channels. So when we destroy those one-way payment channels, we effectively just do replace by Timelock. You'll see the very first Bitcoin transaction, its expiry time is now 99 days, and the following two transactions is 100 days. And we keep doing this over and over, and we can just, keep destroying one-way payment channels off-chain. Now, what's really cool about this construction is that we don't reach present time very quickly. It's really a function based on how many nodes you have in the invalidation tree. But it's very clunky, and it's very complicated. So raise your hand if you'd want to implement this. No one here would want to implement that. I wouldn't, it's crazy. But it works. That's sort of the best we had in 2014. Now, hopefully I got the message across that to try to get rid of that expiry time, or to alleviate it, and the support bidirectional payments was actually really hard to do in Bitcoin. We had to think of these crazy constructions to really get it to work. And Lightning came around and just fixed all of that, in a sense. They support bidirectional payments. There's no real limitation on the throughput. How did they do that? All within Bitcoin. So at a high level, Lightning works as the following. We have the current state, which is just the balance of Alice and Bob. Okay? So when Alice pays Bob, both parties need to cooperate. It's a bit like a two-phase commit. What they're going to do is agree the new balance. Okay? So they're both going to sign off on the new state with the new balance, and then they're going to revoke the old one. And that's exactly how we do a Lightning payment. We agree the new state, then we revoke the old one. What we end up with is a bunch of revoked states. There's no order to them. And one state that represents the current balance of both parties. Now, in practice, that state's actually a bit quirky for Bitcoin. Okay, there's two transactions that represent the same state, and it's asymmetrical. There's only a transaction that Alice can broadcast, and there's only a transaction that Bob can broadcast. But at a high level, that's what's going on. Okay, now the question is, what happens if you broadcast an old state? What if I try to broadcast a state where I'm trying to reverse a payment to Alice? It's being revoked. I send that out. It now triggers this dispute process. There's now this fixed time period where Bob could respond and prove it was a revoked state. Okay? If he can provide that evidence, which we call a justice transaction, he gets to claim all coins in the channel. So that's really cool. If anyone tries to broadcast a revoked state, it's provable. You can prove to this arbitrator, this blockchain, that it was revoked, that it represents an older state, and you can claim all coins in the channel. So we call this replaced by revocation. Okay? You're updating the state of the channel by revoking it. And then later on, you can prove it was revoked. Okay? So what information do we need to prove that an old state was actually revoked? Okay? So typically, the parties to store this pre-image, although I read the Bolt standards today, and they're not actually using the pre-image, but I'm not going to talk about that. At a protocol level, you just stick with hashes and pre-image. But one issue because of Bitcoin is that the Watchtower, they have to store a pre-signed justice transaction. Okay? So what would normally happen is that if I'm Alice, if I see a revoked state, I get this small secret, it's 32 bytes of data. I create the justice transaction, I sign it, I broadcast it out, and then I prove it was revoked and I get the coins. Alice can just store a hash, or even a hash chain. It's very minimal what Alice has to store. But because of the way Bitcoin's designed, as in Alice has to sign this transaction, she has to give a pre-signed justice transaction to the Watchtower. And the Watchtower has to store this for every single revoked state. So every time there's a revoked state in Bitcoin Lightning Network, the Watchtower now has to store a corresponding justice transaction. What does that mean? That's order n storage for a tower. If you do 1,000 payments in a Lightning channel, the Watchtower now has to store 1,000 pre-signed justice transactions. So right now, Watchtower is not that practical for Bitcoin. And that's really frustrating because that's what I'm trying to build as a company. That's how I know about this. Okay, so what are the lessons here, really? We had replaced by incentive, there's limited throughput. We had replaced by Timelock, limited resets, or you build this funky construction to try to get around that, but then it still has an expiry time. Then we have Lightning channels, which is order n. It's cool because there's no throughput limitation, there's no expiry time, it could remain open forever. But right now, because of replaced by revocation, there's order n storage for justice transactions. So Watchtowers are not yet practical for Bitcoin. But this is annoying, actually. Because what you start to realize is that every time we build a new channel construction, we're not really solving channels. We're mostly fighting with Bitcoin to make it do something that it really doesn't want to do. If you think about Satoshi Nakamoto, he never envisioned how payment channels would evolve. He never envisioned what you would need, what components you need to put into the currency to get this to work. Okay? And there's a bunch of problems that really do emerge. And the main issue, if you just ignore most of this slide, is that the state and the transaction are actually intertwined. The transaction is the state of the channel. One issue because of that is now you have the fee is prefixed. When Alice and Bob agree the new state of the channel, they've now agreed to the fee up front. If there's network congestion, it's really difficult to get this into the network because the fee wouldn't be high enough. You'd have to rely on child pays per parent, but then you need an output dedicated to that, which I don't think is implemented yet. So fees are fixed. That's a pain in the bum. Transaction malleability was a pain in the bum until SIG was implemented. So Lightning wasn't compatible with the network until 2017. And Watchtower is a problem. Watchtower doesn't really work yet because it's order n storage. Yeah, we can ignore that for now. So basically, one of the reasons why we've ended up in this situation is because in Bitcoin, you can only do a single state transition. What's a good example of this? Think of Lightning. When I broadcast an older state, that was the only state transition that was allowed. I can't update that. I can't say, actually, there's a later state. All I can do is prove it's revoked and send the coins off. So the question is, if you could support more than one state transition, i.e., if I could prove there was a later agreed state to the blockchain, could we simplify the entire process? Now, what I'm going to mention, there's also one other Lightning problem. And this is again because of replaced by revocation. Make sure your Lightning node doesn't crash. Okay? Someone asked a question about this earlier, what do you need to store if you run a Lightning node? You need to store enough information to prove a state was revoked. And you need to store the latest state. If I crash and I lose that information, I can't broadcast an older state because they can steal my money. So I have to wait around for them to broadcast a state, and they can broadcast anything they want. So an accidental crash is the equivalent of malicious behavior. And that's not nice. If there's an accidental crash, we should be able to recover from that situation. So basically, when you design this for Bitcoin, over the past 5 years, this is how it's felt. You're in this constrained environment trying to get this to work, and it sort of works, but it still has a bunch of problems that could be fixed. Okay? So a lot of my work recently has been in Ethereum. Now, I'm not here to pitch Ethereum, but what I'm going to mention is that what if the scripting facility was a bit more expressive? What if you could support more than a single state transition? Could we build much simpler channels? And we can. There's writing for payment channels world, but then you have state channels where we try to take this a little bit further. So instead of payments, you could do gaming, voting, auctions. You could just take a smart contract, take it off chain, and run a smart contract here. But how do we get this to work? Okay? The state replacement is really simple. Every time we authorize the new state of a channel, we just increment the counter. So you have Alice's signature, Bob's signature, the state of the channel, the balance of Alice and Bob, and this counter I. I sign the new state, I give it over. He signs a new state, he gives it over. And we just keep incrementing this counter. Whatever state has the largest counter is considered the final state of the channel. Now, what if there's a dispute? Okay? What happens is that any party can trigger a dispute. Alice and Bob, they say, nope, I don't agree. That's triggered the dispute process. Now there's this fixed time period where Alice and Bob can send the latest state of the channel. Okay? Maybe Bob will set an older state. Alice will send the latest state. Whatever state has the largest counter is considered the final state of the channel. At the end of it, we can resolve the dispute. Whatever was the latest state with the largest counter, that'll be the final balance of both parties. Now, the important bit is, why is this really cool? State channels are just like Lightning. There's no expiry time, no transaction throughput limitation. We don't sign transactions. We sign a commitment to the state, completely separate from the transaction. So now we have dynamic fees. We can pick any fee we want when we broadcast. It's really easy to support Watchtower services. It's order one storage, store the latest state with the largest counter, and there's no clunkiness. It's super straightforward to implement. Now, what I want to highlight is I'm not here trying to bash Bitcoin. Actually, there's real attempts to get this style of dispute process in the Bitcoin. The Lightning developers are well aware that this is a much better way to build channels. And they want to get this in the Bitcoin. So as you just seen in the previous talk, that's the next slide. This is Rosebeef's slide. So I attended his talk for Watchtower BPS in 2018. And if you look there, they want to redesign Lightning to do exactly this, replaced by version. Where in Bitcoin, every time we sign the new state, we just increment that counter. This is from, This is for Bitcoin. This is for Bitcoin 2018 BPS by Rosebeef. So he works at LND, Lightning Labs. No, I think they're going to try with a sock fork. If you have sig hash no input, you can do this. So this comes to my next slide. So that's the L2 proposal. If you look at that diagram, every transaction has a counter. So when you trigger that dispute, you have this temporary state where you submit the transaction with the latest counter. Eventually, the transaction with the largest counter is the latest state, and then it'll pay both parties. That's the L2 proposal in a nutshell. And what they need for this is sig hash no input. If this is in Bitcoin, you can then get these really cool, simple payment channels. So the whole point of this talk was, if you don't like Ethereum for whatever reason, that's fine. But what's nice is that having this expressive bottom layer really simplifies the process for designing protocols. And while Bitcoin's really simple, oh, that's the next slide. Okay. Here, of course, in Ethereum world is not all rosy either. Who's heard of DevOps 199? Some people have. He just went and destroyed a contract and locked up $200 million. So it's not very rosy there either. But the whole point here is that we should be making it as easy as possible to design protocols in Bitcoin. While Bitcoin script's really simple, and Bitcoin script is really, 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 really simple, it actually pushes some complexity to the upper layer when you design these protocols. And we've just seen the whole history of off-chain payment channels, and every time we improve the payment channel, it gets more complicated. And it's just because the bottom layer isn't built to support that. So, this needs to be fixed. Let's advance Bitcoin. Let's get Zcash no input in there and actually get really cool payment channels out of that. So that's basically the end of my talk. Oh, I think I just destroyed the projector. Just in time. Yeah, awesome. Should we do Q&A or any questions? Yeah.
Hello.
Hi.
Yeah, I feel like you're trying somehow to, first of all, I think you have a bit of a bias towards Ethereum considering they're sponsoring you, because I don't feel like it's really fair to say that the design of Ethereum is something good like that. That's a flaw, because the more complexity you have on the base layer, the less secure it is. Can you talk a bit about that?
I can't talk about that. So a lot of the vulnerabilities we've seen in Ethereum.
If you can emphasize the trade-offs, actually, pretty much, yeah.
Yeah, so a lot of the problems we've seen in Ethereum is because the EVM is really quirky. And the quirks really shouldn't be there. So Ethereum's too expressive in that sense. But on the other end of it, Bitcoin's too simple. And because it's too simple, it actually pushes that complexity to the upper layer. And I think a good way to think about all of this is, and I tell this to my students, when you design protocols, you should imagine there's this ideal functionality, this ideal trusted third party who will implement your algorithm as expected. What's really nice is that smart contracts, for the most cases, do that. But for a long time, people would design these algorithms, port them to Bitcoin, and they wouldn't really work. So then the whole point of the research was to fight Bitcoin to get it to implement this algorithm. And for the past 5-6 years, that's what we've seen. And that's really frustrating. So that's why I like Ethereum. I don't like it because, the EVM's better. The EVM has a bunch of problems that needs to be fixed. But it's much easier to implement these algorithms or these trusted third parties.
Fair point, but I don't know if that's still a good trade-off, because Ethereum has so many problems. No one is running nodes. I don't want to be mean, but I call Ethereum a dumpster fire of a project, if you may, and because that's all just because of all they made this trade-off, and it's not really decentralized. There's nothing good about it. So yeah.
What's decentralized to you?
Bitcoin is the only decentralized thing we ever have. Yeah.
But what's the properties of decentralization?
Well, pretty much running the nodes. That's a big part of it. Being able to run a node and being able to vote on the network and have a say, and then say, I want to run this specific part of software because then this makes sense. That's the most important thing, and we can't trade off for nothing, I think.
So as public verifiability, as in, can I hold the miners accountable? And that's the whole motivation for off-chain.
Right. Okay. Fair point. I don't know if that relates, but yeah. Thanks for the answer anyway. A nice presentation.
Awesome.
Can I actually? I'll ask.
Yeah.
I was going to ask a similar question, and we've had a few projects here recently because I think obviously we started out as Bitcoin networking group, so that's something which I appreciate. But also from the beginning, that the expressiveness of Ethereum contracts or smart contracts to me seemed like a problem. And I think we've seen projects. We had Zen Protocol last year. We had Blockstack, and they were talking about simple contracts. We had Cardano recently, and they were also talking about that the kind of more constrained model. And I think Digital Asset, which are kind of reviving soon,
Yeah.
and we're having here talking about kind of DAML, their markup language. Is there a middle ground where we have something which is kind of widely accepted as a kind of viable contract for certain use cases, which are more restricted than something like a Solidity smart contract, but also have a little bit more expression than something like a Bitcoin opcode?
I think that's what people are going towards now. So let me talk about some of the other trade-offs. So what's really good about Bitcoin is that their focus is, you know, what do they call reorg safety. So if there's a 100-block reorg, your transaction should always execute as you expect, you know, because you commit to the output of the transaction. Where in Ethereum, you don't get that. You know, if there's a 100-block reorg, all my transactions could then fail. So I have no guarantee what the execution is going to be when the block, you know, when the transaction gets in. So I think what's really important is that over the past 10 years, we've seen the problems that emerge in Bitcoin. We've seen the problems that emerge in Ethereum. Now people are trying to pick the best of both worlds, put them together, and try to get a more expressive platform. My other worry is that a lot of these projects are pushing for formal verification. You know, that's one of the things for Zilliqa and Cardano, etc. But my big fear there is that not many people can actually do formal verification. You know, you need to do a PhD to understand formal verification. So my big fear is that that's not really going to take off anytime soon. So the question is, what are we going to be left with? You know, yeah. Dogecoin, Elon Musk, he's the former CEO of that. So I don't really have an opinion on where the middle ground is. I think we're just going to find that empirically.
Hello, thank you for the talk. I was just wondering, if you had a series of revoked transactions, how do you stop someone from broadcasting a revoked transaction and then maybe using a subsequently revoked transaction, but not the most current one, in order to try and claim all the coins?
So the thing about Lightning is that all the revoked transactions are equal in terms of there's no order. So the Bob, if we have a payment channel, your Bob, for example, you could broadcast any revoked transaction you want. And it's up to me to find the evidence to prove it was revoked. So I can't stop you in broadcasting the revoked transaction. Is that the part of the question, or? Oh.
Is there any way that I could then prove that it was revoked, and then by proving that that transaction was revoked, claim all the coins? Which I think
yes, that's exactly what happens.
Yeah, but without the actual current transaction, a sort of intermediary revoked one. So
this is the thing, is that because of the way Bitcoin's designed, you can only do one state transition. So if the revoked one gets accepted, the current state can no longer be broadcast. That output's been spent. So all you have to do is prove it's revoked and then get all the coins. That's the only path you can follow. And that's really frustrating. You know, in the ideal case, there should be no penalty. You can just say, this is the latest state that everyone deserves, get the coins. Which is sort of what they're going for with L2.
Going back to this issue of benefits and problems with scripting languages, to me, the big cutoff point is Turing or non-Turing complete. So do you think people are moving towards a more expressive non-Turing complete language, more like a domain-specific language that enables people to see and read things easily, not necessarily to be formally proved, because as you rightly pointed out, that's a big issue. If you've got a PhD, yes, you can formally prove stuff, but sufficiently expressive that you can read it and see what it's
I think there's 2
intended to
points I'd like to mention here. Is that I would disagree that Ethereum's Turing complete. You know, I think that gives developers the wrong mindset. If you say it's Turing complete, they think they're going to build a DEX on Ethereum. And that's not going to work very well because the fees are too high. I think what's much better to look for these blockchains are more like a settlement layer, or that you prove something happened. So that's why everyone's really excited for snarks and starks. Because what I can do is I can prove a computation is correct without actually doing the computation. So this is no longer a world computer. You know, you don't do the computation on the blockchain. You just prove that the computation actually happened. And that's really nice. And that also follows the Bitcoin vision as well. You know, that's one of the motivations for layer 2, is that we do these transactions locally, we do thousands, we just send the latest balance. Blockchain, I mean, the blockchain doesn't care that we did that computation. It just cares about the output of it. And that's sort of where everyone's going now. So what I'd imagine in the next 10 years is that the base layer could be very simple, you know, it accepts proofs, runs simple programs, and everything else happens off-chain. And that'll be really exciting if that works. You know, that'll be so powerful.
Do we have any more questions in the room?
Thanks, mate. Very nice talk. I think you flagged understandability and clunkiness as a kind of variable in whether people will actually use these things. What are your thoughts on how close Lightning is to being a kind of protocol that everyday normies will use?
So I wrote a blog post about this. You're all welcome to read that blog post, by the way. I think what we're going to end up with in the next 5 years is that I don't see Lightning being used for payments. What I actually see Lightning being used for is liquidity and routing payments between hubs. Why do I say that? Payments not very good, or Lightning is not very good for one-way payments, but it excels at bidirectional payments. It's amazing at bidirectional payments. On the other hand of it, what we now see emerging are these commit chains, like Plasma and NoCust, and there's a trade-off here. So if I run a commit chain, the idea is that I collect transactions. People are sending me payments via my service. I put a hash in the blockchain periodically, and I commit to everyone's transactions. But as the hub, I'm non-custodial. You don't have to trust me with your coins. You deposit coins in, you start sending it to your friends via me. Completely non-custodial. What's really exciting about it is that with these commit chains, as the operator, I don't put up any money. To facilitate payments in this commit chain, I run the service for free. Everyone else puts in coins, and we can actually move the coin from Alice to Bob. Where in Lightning, we don't move the coin. We redistribute to deposits. And that's really clunky for payments. But as a commit chain, that excels at payments, but is not very good for sending payments from hub to hub. Where Lightning would excel at that. So for me, what I envision is this Lightning network emerging that's going to route payments between these non-custodial hubs. And most of the payments are going to probably happen in these hubs, but they're all non-custodial. And that would be really exciting if that actually evolved. So I hope that answered it.
Yeah.
Awesome.
Thank you. Any more questions before we wrap up and eat pizza?
Thanks. Do you think we're missing some kind of transactional item?
Transactional item.
Like currency or a coin, or like literally to transact with?
I mean, you've got Bitcoin and ETH. I think that's enough.
Okay.
I don't really see the point for tokens. That's my issue there. I'm a bit of a maxi that way.
For common take up, for just so that people. Because people understand.
Oh, you mean like a
physical
stable
items.
coin? Oh, okay. You mean as in like a physical Bitcoin? People have been doing that at meetups. I've got like a little coin that has like Bitcoin on it. I think it's like $10 worth, but there's some Bitcoin there. I think that would be useful, but I don't see it working. I mean, Bitcoin. I mean, all these cryptocurrencies are for a global stage. They're for cross-border transactions.
But for sub-channel off-chain.
Off-chain. Yeah, that would be the same. I don't think we need a physical coin. I think what we need for off-chain are just really good user interfaces and being able to onboard users really well. So I spoke to someone here earlier, and he's a non-techie, and he was like, how can I help the Lightning Network? And I told him, set up a Twitch channel and go through the process of setting up a Lightning wallet. So everyone can see the problems you hit, and then someone else can go fix it. So who raise your hand if you'd like to see that? Who would like to watch a live feed of someone setting up a Lightning channel? People here would, I think it'd be awesome. I want to really discover what are the hurdles to real world adoption. And that's going to be the hurdle. How easy is it to join Lightning or join Bitcoin or cryptocurrencies? I hope that answered it a bit, or you look a bit lost.
Thanks.